Now, I think with this we should now interpret the sampling process. We have just started with the conventional Dirac-Coombe sequence and then linking that via the samples. Now, let us actually interpret sampling. So, the sampling process converts a continuous time signal into a signal of discrete time. Basically, I have a continuous time signal, and when I sample I just get some numbers, right. I just get some a sequence of numbers. Now, here is the basic idea in the sampling theorem. And we saw that idea when we started off with Shannon's basic idea, right. So, if a signal S of t, this is not delta, if a signal S of t contains no frequencies outside B hertz, it is completely determined by its values at a series of points I could make it as a sequence of points here. Spaced 1/2b seconds apart. I think this is a very important result. That means for a given sampling rate Fs, perfect reconstruction is guaranteed for bandwidth capital B, which is strictly less than Fs upon 2, right. If Fs is your sampling rate, then your perfect reconstruction is guaranteed if your bandwidth B is capital B is basically less than Fs upon 2, right. So, here determined by its values at a sequence of points spaced less than 1/2b seconds apart, because this is in time, right. In frequency it is greater, in time it is less. Now, let us consider the periodic summation of the spectrum of S of t. This is basically k equals minus infinity to plus infinity S of f minus k times Fs where Fs is 1 upon t, which is basically your sampling rate. And you can interpret when k equals 0, it is a baseband, right? It's a baseband. Now this is written in the form n equals minus infinity to plus infinity t times s of n times t e power minus j 2 pi n times capital T times f. We saw this in the last step when we derived it, right. We started off with a periodic sum, and then we interpreted how we can write it in this form, right. If you just go 2 slides here, this is exactly the formula, right. So we write it in this form. So what do we see here? I mean basically copies of S of f multiples of Fs translated are essentially added. This is what we mean by this periodic sum, right. I have a spectrum, I take a translation in multiples of Fs, right, then I add the copies. Now for band limited signals, that is x of f is equal to 0 for frequencies outside B and sufficiently large Fs, it is possible for the copies to be distinct from each other, right. You can sort of interpret this as follows. You have some spectrum, and ideally you would want to have copies that are distinct, right. I mean this is, you can imagine this is a copy and the copies have to be really distinct. Otherwise if you get them overlapping, then you have troubles. You see the interpretation of this, and this is your aliasing. Okay. Now if the Nyquist criterion is not satisfied, adjacent copies overlap, and this will imply aliasing effect. So you can think about this overlap, and this is Okay. Now, this is one of the reasons why normally people like to limit. So, even if the bandwidth is really not limited, you would want to limit the band by putting an anti-aliasing filter or typically a low pass filter before you sample. This is very important. Now, let us derive the interpolation formula. Now, this periodic sum copies of the spectra can be used to recover S of f, that is with k equals 0, right. So, we can say that S of f is some h of f with S periodic sum of f, and I say h of f is defined as a filter which is 1 for frequencies less than b and 0 for frequencies outside fs minus b. This is very critical, and the crossover point happens when b equals fs by 2, right. These are the Nyquist rate. If I am not at Nyquist, then it is fine. Okay, then it is fine. We do not have anything to worry, but if we are at Nyquist, then we have to be worried about. Okay. So, now h of f is basically a rectangular filter which is basically 1 inside the band and 0 for all frequencies outside, and I have deliberately left the point when it is equal because it is a discontinuity point. Okay. But if you want, you can fold it into one of these inequalities. Now, x of f is rectangle f upon fs times s periodic sum of f, and we linked what this periodic sum is. So, this is a rectangle T times f, because capital T is 1 upon fs, times summa n equals minus infinity to plus infinity, and we can write this as periodic sum as T times s of n times capital T with the modulator. We derived this earlier, right. So, now we fold everything here. So, this is basically summation n equals minus infinity to plus infinity s of n times t times t times rectangle T times f times e power minus j 2 pi n times capital T times f. Looks really messy at this stage. It looks right. I am just folding this constant inside the summation. Now, look into this It is basically the Fourier transform of sinc t minus n times capital T by T. Okay, and now I think you can see, you can almost see that how the result is correct, right. I mean, you just take the inverse Fourier transform on both sides of this equation, we have x of t equals summation n equals minus infinity to plus infinity x of n times t sinc of t minus n times capital T by capital T. I mean, again, because Fourier transform is linear, right. So, just right, and so Fourier transform is linear. So, therefore, I think I have to use a variable s which is consistent here. I think I can make this s of f so that it is consistent with the rest. Okay. So, so now this is fine. Okay. So, this is going to be s and this also happen. Okay. So, basically to get the baseband s of f, I use this relationship and then I expand the periodic sum in this form, right. I fold the rectangle function into the summation, right, and I can interpret this as basically the Fourier transform of the shifted copies of the sinc function, and now you have summation over several Fourier such transforms, right, summation of something with the Fourier. I take the inverse Fourier transform, because it is linear, it automatically stems. Okay, and this is basically your sinc interpolator. So, this is the reason why people talk about an ideal low pass filter towards reconstruction, right, and the ideal low pass filter is essentially doing this job of sinc interpolation. Okay. Now, I think one of the important discussions related to sampling would be the following considerations. So, I would say these as other considerations. A, the sampling theory can be generalized when samples are not taken equally spaced in time. So, so far we considered samples which are 1 upon 2b apart, right, 1 upon 2b seconds apart, if b is your bandwidth in hertz. Now, samples need not be equally spaced. So, there is work by Henry Landau on non-baseband non-uniform sampling. So, you can kind of generalize the sampling theorem assuming uniform sampling to a more general form with non-uniform sampling or irregularly spaced samples. And of late there is recent well developed theory on compressed sensing, or it is also compressive sampling. The idea is this allows for full reconstruction with sub-Nyquist, this is very important, sampling rate for signals that are sparse, that is they are compressible. So, what it means is basically you have low overall bandwidth but frequency locations are unknown rather than everything in one band. So, these are some variations of the sampling theorem, right, and one can generalize this from 1D to 2 dimensions when you can imagine signals in space, etc., in 2 dimensions, picture signals, etc., right. Color, I mean color is really, color can be continuous. What we think is 256 or 6556 36 65,000 odd colors, etc., it is our perception, right. Color can be really continuous because all of these are frequencies which are basically continuous. And if you think about an image, that is essentially basically can be sampled from continuous picture in space. Okay. So, I think these are some considerations, and one can deal with sampling theory completely from scratch. I mean it's probably a semester of coursework, right. But in the interest of time and towards this course, I have just given you a brief idea of the sampling theorem, the Nyquist criterion, and the interpolator, the ideal interpolator, and the derivation of these derivation of the interpolation formula, right. Starting from sampled signal, how can you reconstruct the continuous time signal. And now once we understand what sampling is, how you can get perfect reconstruction, we are interested in sampling rate conversion as part of multi-rate signal processing, that is given digital samples which are sampled at one rate, how can we convert from one sampling rate to another sampling rate without going back to to the continuous time signal, and that is the focus of the study for the rest of the modules. Okay, we stop here.